Right, line A6, learning task 7. We are on to the fourth of our circuits that we have inside of here. This is going to be the light dimmer that is using the UJT, or the uni-junction trigger, that we're going to have. Sometimes referred to as uni-junction transistor, but it is going to be using this thing to go and give us a little send of voltage, a small pulse that we're going to go and have. I want to actually isolate this circuit into two distinct components that I'm going to go and have. It's actually three distinct components. But before I do that, we first have to go and fix this thing, because once again, that light was in the wrong location, and we have to move that light over so that it is going to go and be in line with my actual controls component, which is going to be this triac that we're going to have over here. And then this section is just going to get spliced right through. The three sections that I'm going to go and take a look at are going to go and be my AC section. So all of these devices over here are going to go and be seeing AC. Okay, those are all going to be AC components that we are going to go and have. Then what we're going to do is we're going to come off of that AC. I guess we should just carry this from here and here. That's all going to be AC up to there. From that point, we are then going to go and transition into DC. And so this is all going to be pulsating DC that we're going to go and take out from here and to here. And then from that point, we're going to go and drop down into a regulated value of DC. Everything from here on in is all now going to go and be a DC regulated 10 volt section over here. I'm going to go through how each of these components basically is switching over inside of us or in a second here. But we do have a couple of sections. So when we're talking about the 10 volt section, we're talking about those lines that are highlighted in yellow. When we're talking about the rectified DC section, we're going to be talking about generally the green one, although this is rectified DC as well, I recognize that. And when we're talking about the AC, we're going to talk about these blue sections that we are going to go and have over here. Let's start by erasing all of that, and then let's go through these components one at a time. First thing that I'm going to go and talk about is just the light itself. If we take a look at the light, we see that the light is attached to that AC supply over here, and that it is controlled by an AC bidirectional device. We have got this triac over here. What does the triac need to turn it on? Well, all it needs is a little pulse that is going to go and happen. And anytime that it gets a pulse, it's going to be able to kick on and start to go and operate. What do I have over here? Well, this thing, this sprigged item is just going to be what we call a pulse transformer. It's designed to go and allow us to take something out of the DC section, the 10 volt DC section, and then pass it through into the AC section without any direct electrical connection. It's really handy to be able to go and use this. Take a small pulse, kick it out of one section, send that over to the opposite section. Because this is an AC section, this is going to be acting as if it were an AC transformer, but it's going to be relatively small because the amount of volts that we're going to have dropped over top of this is going to be tiny, not enough that it's going to go and cause a lot of damage inside of the circuit. And anytime that this is shut off, there would be no complete path for current flow, so we wouldn't have to worry about this transformer somehow feeding anything back into the rest of this circuit over here. This is really going to only go and kick power out of the low section into the high section. Okay, let's start by assigning all of our DC polarities. We know that coming in here, we got AC, and then if we take a look at this, when my AC comes in, we're going to see which side passes the positive. If we take a look, D3 would be blocking because it's got the cathode. D1 would be passing, so it could pass a positive through there. And if we go and take a negative in on the other side, remember we can't have one without the other, we would see that a negative would be able to be passed through this D4. So I've got a positive and a negative rail that I'm going to have on that section over there. I'm actually going to go and move this entire drawing just for a second, just bring it a little bit lower. Good enough. Just so I got some room to go and draw up top. Taking a look at this, now that I know where my positive and my negative is, I'm then going to go and analyze this little section over here. This is what we refer to as a Zener voltage regulator. And a Zener voltage regulator is going to go and drop the Zener voltage over top of the Zener, and it is going to go and drop the remaining voltage over top of whatever we have for like a sloughing type of resistor. So coming into this section over here, we're going to go and have pulsating DC that we are going to go and create. So I'm going to draw it actually a little bit bigger so I can very carefully. Okay, so that's what we have at this point over here is going to be that pulsating DC. What we're going to have is we're going to start this DC value. It is DC because it's all in one direction, even though it is pulsating, and then it's going to start out at 0 volts and it's going to go and rise. Well, for a zener is going to go and block until it gets to a certain amount of voltage. Then it's going to go past that voltage, but it's also going to maintain that voltage. It doesn't just like drop away and become like a diac where it drops down to a smaller voltage. It just maintains that voltage over top of it. So as we rise, we're going to go and hit the point where we're going to hit that 10 volts that we are going to go and have. We're going to call this here 10 volts, this line. And we're just going to describe it all the way across our drawing there. When we hit 10 volts, this zener is going to hold at 10 volts. And then this part of the circuit is going to go and drop the remaining amount of voltage. See how it's in series with the zener over here? Remember that we have to go and drop all of our voltage. Kirchhoff's law of voltage says that the sum of all voltage drops is equal to our source value of voltage. And over here, we've got a source that's getting all the way up to 170. I know it's not to scale, but it's up to 170 volts at the very peak, which means that this resistor over here is going to be dropping everything from 10 to 170 volts. That's going to be across it. This is why it's a high wattage type of resistor that we have inside of here, and why it's got a specific value that's assigned to it as well, the 6.8K ohms over here. We're just going to go and raise our value of volts until we hit the 10 volts. Once we hit the 10 volts, then the zener conducts, it locks in at that point, and it maintains 10 volts. Well, if I take a look at this zener, everything else from here on downstream is in parallel with it. And if this stays at 10 volts, that would mean that all the rest of this is also going to go and stay at 10 volts. So this section of the waveform, this whole top section, is just basically going to be cut off and burned off through this resistor over here. It's a waste of power, but we do need it so that we can go and have this 10 volts. Now, a couple of things that I want to go and look at now are going to be this waveform that we have across the zener. The zener is going to see the rise, then it flattens out, stays level across, and then there is a drop where the main waveform drops. Rise, and then a drop. Rise, and then a drop. Rise, and then a drop. And this is really important for us to go and recognize that we have this, rise and drop, rise and drop, rise and drop, because that means that we're going to hit these points right over here, which are going to be 0 volt points. And 0 volt points are really handy for us because they're once again going to go and provide commutation. This 10 volt system that we have, going into the 10 volt section now, we've got a negative and a positive. We should recognize these two sections over here as being an RC timing network, a resistor and a capacitor. The amount of resistance we have in there is going to determine how quickly we charge that capacitor up to. We also have got this section over here, which is half of a transformer, but it is in DC. And how does an inductor, that's half of a transformer, operate in DC? Well, it acts as if it wasn't there, as if it was a short circuit. There's a small opposition just during any time that it's changing, but then as soon as the current stabilizes through it, it's going to go and lock in and act as if it were just a conductor. So 99% of the time, our circuit just really doesn't even notice that we have got this little section inside here. Really what it's going to see is it's going to go and see this. And remember that these are the UJT, which are made up of a contiguous channel of material. We're going to go and have our T2 and our T1 off of it, and then we're going to go and have that small P-type of material that's going to be inside of here if this is an N-channel type of UJT. Because it's all a contiguous piece, that means that any current will travel through this thing, up and out to the other side. So there'll always be some leakage current through there. This is fine, because if I take a look at this DC section over here, I see that this is going to go and have current that's going to continuously be traveling through here. This over here needs to go and get to a value of voltage that's going to be a slight bit more positive than approximately 2/3 of this, or what we refer to as the intrinsic standoff ratio. So let's go and say that this is going to be at 7 volts perhaps. I don't know if they actually give you a value inside of your book, but maybe they do. Hold on, let me go back to my book and take a look. Yeah, they don't give us anything inside there. Perfect. So let's say that this value that this is going to trigger at is going to go and be 7 volts, between 0.5 and 0.8. So all we have inside of this circuit is we've got this buildup of electrons start to build up. They start to drive away from here, and from here they're going back out to our source. That arrow, I just drew that to show the 10 volt, not a direction of current. So those electrons are going to build up. As this voltage rises, we're going to eventually hit that point where we hit 7 volts. Once we hit 7 volts, remember that what's actually happening inside of here is we're breaking down a depletion region, a barrier region that is around the outside of that PN junction, which means that this is now going to be forward biased and able to go into conduction. So this is going to be the more positive end, this is going to be the more negative end, and because it has gone into conduction, it is going to act as if it were a switch across here. Well, what do I have to switch? I see that I've got a bunch of electrons stored over here and a bunch of holes over here. So all of these electrons are going to flee, whoosh, and they're just going to go and in a mad rush charge right through there because there's hardly any sort of resistance in this path. So what we're going to have is we're going to have this point where it breaks over and there's going to be, boom, that rush of current that's then going to go and taper off until it falls below that holding current. That current that I'm going to go and see, and you can go back to the UJT section in Learning Task 6 if you want to go over those again, but that current is going to come through as a spike. Well, if I get a spike, that means I've got rate of change, and for a transformer, transformers only react on rate of change when the voltage is changing. Is this voltage changing? Yes, it's changing quite rapidly. So is it going to get picked up by this side? Absolutely. This side is going to do the same thing where it's going to go and have a spike because it's in a transformer. It's going to be the opposite direction. But it's going to go and have a spike that is going to happen, and that is going to go and gate this system that we are going to have over here, turning on this transistor. Or sorry, the triac that we are going to have here. When it does that, we're then going to be able to flow current through here. So we'll have current that's going to go and pass through, lighting up our light. Once again, the amount of resistance that we are going to go and have is going to determine the amount of time that it's going to go and take for this to go and charge up, hit that intrinsic standoff ratio, which is then going to give us that bump of current through here, which is then going to give us our trigger. Less resistance means faster charge up, means more light, because we're going to have less waveform that we're going to end up cutting away out of that AC circuit. It's a pretty cool little system over here. Anytime that we do go and commutate, remember how we said that on that DC section that we can get that commutation? I'm just going to see if I can grab, I don't know if I can grab that one or not. Can't grab just the blue one. Oh. Anytime that we get that commutation that is going to go and happen, we are going to go and drop our value of voltage inside of here on that blue little Zener line that we had. When we do that, we are also going to go and discharge this cap. This cap is then going to go and release, and it's going to be able to transfer back through here. Remember that this diode acts as if it were a regular diode. Anytime that we have got, positive value of voltage over top of it. If I were to go and take a look at how I'm going to go and charge these up, this cap is going to go and act as if it were a source, which is going to be delivering my electrons through it. So we'll be able to discharge and clear those off. Just allows us to, once again, go and reset what we have inside of this circuit. Fun little circuit. Okay, we're going to move on to another one that is going to be a bit more complicated. The last one's going to be our triac motor starting switch.